So we're going to look at the gravity model, which is part of traffic forecasting, and the main concept behind the gravity model, and it really is similar to, for instance, the gravitational pull between planets, and we're doing the same thing, but in this case we're looking at trips and trip producers and attractors and what the relationship is there. And the underlying assumption is that the likelihood that a trip occurs is a function of the distance and the trip attractiveness. And so that's what we're going to use this equation for. Of course, there's many more sophisticated models in traffic forecasting. This is a simplified model just looking at this one perspective, but there are lots of other things that we can consider if we're actually doing traffic forecasting. And so what we're going to do is we're going to solve for the total number of trips from TAZ-A to TAZ-B, and where TAZ is the traffic analysis zone. And so this is what we're going to use the equation for. So we're going to start with the total number of trips from TAZ-A. So how many trips does TAZ-A produce? And we're going to look at distributing it, and essentially we're going to weight this by the other zones and factors for the other zones. And those factors are the total number of trips attracted from TAZ-B, the distance or the travel cost, and this is also known as the friction factor. And a lot of times the value we use for that is 1 over the travel time from zone A to B. And then we have a socio-economic factor, a parameter that is going to help us balance the results. And what it's doing is helping us measure the relationship and the likelihood between these two zones, A and B. So we're going to take a look at an example. We're told we should use the gravity model to estimate the number of trips between a university campus and zone 2 during the PM peak hour. The university campus is expected to generate 1,100 trips during the PM peak hour, and it will be distributed to these 3 traffic analysis zones. Of course, this is a very simplified example. In reality, this would be much more complex and labor intense, but we're just looking at a few zones here. So we have some data on each zone. We've got the travel time in minutes. We've got the number of trips attracted during a typical PM peak hour. That doesn't mean from our zone in particular. It's just that's what these zones are attracting during the PM peak hour. And this is going to help us give us an idea of how it's going to influence how those 1,100 trips from our campus are going to be distributed. And then finally, there's a socio-economic factor between the campus and each zone. And the higher that value is, the higher that factor is, the more relationship there is. And so, for instance, if we're thinking about it in the context of a university campus and how we're going to distribute those trips, those would be things like, are there affordable housing for college students? And so the higher that factor is, that's telling us there's a strong relationship between these two zones, campus and the zone, and that there's housing opportunities there, or there's attractions that they would want to travel to. And the lower values represent lower likelihood or lower relationship between those the campus and that zone. So we're going to set up our table here. So we're going to start with setting up a row for each zone, 1, 2, and 3. Next, we have our distance or travel cost. And I said it's common to assume that your friction factor, F sub AB, is 1 over your travel time. And so this is what we're going to set up here. So for zone 1, our factor is 0.125, and that's 1 divided by the 8-minute travel time. Next, we have the total number of trips. So that comes straight from the table that we were given. So these are the trips that are attracted from TAZ-B. Next, we have our socioeconomic, or our parameter that's going to ensure that the results balance. And so now we have the 3 factors we need. We're going to just multiply these in our next column. So it's just, again, each of those preceding 3 columns, so 0.125 times 4,500 times 1.8 gives us a total of 1,012.5, and we're going to carry that through the rest of those rows. We need to sum that, and we're going to get a sum of 1,226.65, and that's going to be the denominator in our gravity model. So that's going to be an important variable that we're going to use. And essentially what we're going to do now is go back in our next column and divide each one of those individual values by that total. And so that's what we're doing here. And so we'll see that total is 1, and we're apportioning the total trips. What we're going to do is we're going to apportion those total 1,100 trips to each one of those zones based on that proportion. So in the first row there for zone 1, we have 0.825, and that is 1,012.5 divided by 1,226.65. The next one is 201.667 divided by 1,226.65. And our last one is, again, a very small value, 0.01, which comes from 12.4855 divided by 1,226.65. And again, that totals to 1. So this is the proportion of those 1,100 trips we're going to distribute. So our last step is just to multiply that column by our 1,100. And so for zone 1, so our campus is going to send 908 trips to zone 1 is going to be our estimate, 181 to zone 2, and only 11 to zone 3. And this should make sense looking at zone 3. That's the longest travel time and the lowest socioeconomic factor. And so we would expect there's not a strong relationship between the campus and that zone. Whereas looking at the one that's the highest, the 908, it's the shortest travel time, just 8 minutes, and it's got the highest socioeconomic factor there. So we would expect that that's where those trips would be distributed. Because of rounding, we don't end up at exactly 1,100. We're at 1,099, but this is going to give us a good estimate for how those trips would be distributed. Overall, we are asked for between the campus and zone 2, and so the answer there is 181 trips during that PM peak hour.